So how do we get from pixelized maps to cosmology? And then I show the results of the three-type two-point analysis, the angular correlation function, and etc. Okay. Sorry, this is wrong. I have to correct that. So this is a figure that shows how complex, I hope now this can show to you how complex it is to do the complete analysis. And this is a figure that was done by Alex Amon. So you get the images, and you have to do the photometry, and you need the survey selection, then you need the redshift calibration. This point spread functions the atmospheric conditions that changes the shape of galaxies, so it's important to correct for these atmospheric conditions. So you need to know what this thing called point spread function. Then you get the shape catalog. There's some blending because some galaxies can be on top of each other. There are lots of details there. Then you get finally with redshift distribution, you get the the calibration, you get the redshift distribution. So this is your question, how many redshift beings there are. Then you have to model the covariance, and that's what where our group has worked in the year 3, one of the things. And there's a methods paper to define the methodology for the analysis. You measure the two-point function for clustering, for shapes, etc. And finally, you have analysis choices and modeling. You have to check everything on some mock data to see if you can recover the cosmology from some mock data, some simulations that you know what the result is. And then you have to mitigate experimenter bias. You know what experimenter bias is? So we do everything blinded. So we don't know exactly what the shapes are, the angular correlation functions are. We do everything blindly. And only in the end, we unblind. And then we have the final results. And the final results are things like this. So I'm going to show you what the final results are. Okay, so there are several cosmic probes that you can look at DS, but we mostly look at, in this 3x 2-point analysis, it's basically large-scale structure and weak lensing. And BAO is actually separate from the 3x 2. I'm not sure if I have time to show the BAO results. So I'm going to talk about the DS year 3 data, which is the one that we finished and is published. We have more than 30 papers on that. So, and these 3 papers is on the BAO. So the main results are for the 3x 2-point correlation functions. And our group has contributed with the study of the covariance matrix. Then there are results from the baryon acoustic oscillation, and our group has contributed the harmonic space analysis. So all the dark energy survey main analysis is in real spaces, angular correlation functions. But we decided to look at the angular power spectrum to see whether or not they agree, the 2 analyses agree with each other, and if you can add something else. And also, yeah, so we also did some harmonic space analysis with the DS year 3 data. Okay, so what is the 3x 2-point analysis? Again, it's a combination of 3 correlation functions: the galaxy clustering correlation function, the galaxy shape correlation functions, and the shape-shape correlation functions, the shear correlation functions. So it's a self-consistent analysis, because it's only based on DS data, which maximizes the cosmological information and constrains some astrophysical and observational systematic priors in the analysis. And we're mostly sensitive to 2 quantities, and that's why mostly we're going to see plots of these 2 quantities that we're most sensitive to. And what are these 2 quantities? One is the amount of matter in the universe, omega matter, and the other is a quantity which I didn't talk too much. It's called S8. So let me talk a little bit about S8. So there is a quantity called sigma 8. And sigma 8 is the variance of the matter fluctuation in a scale of 8 inverse megaparsecs. It's something that if you remember my my slides on the lambda CDM model is not one of the parameters in the lambda CDM model, right? I never said that sigma 8 was one of the parameters that enters in the lambda CDM, but it's actually a derived parameter. So from the initial amplitude of the power spectrum and all the other parameters, you can get what sigma 8 is in the standard cosmological model. So sigma 8 is something that people talk about a lot, but it turns out that the most sensitive parameter that the DS is most sensitive to a combination of sigma 8 and omega matter. And this combination is this one. It's called S8, which is the combination of sigma 8 times omega matter to the power a half. And why is this why DS is more sensitive to this? Because we make plots like that, and this is sigma 8, and this is omega matter. And this is, you see, these are uncertainties. And in this direction, the uncertainties are smallest. And this is exactly this combination here. So that's why we use S8. So have you heard of S8 before, anyone? Some people call the S8 tension now. In addition to the Hubble tension, some people say the S8 tension. So this is S8. This is the combination of sigma 8 and omega matter to the power a half. Yes?
Related to the power tension?
Yeah, nothing. I only heard S8 tension. But there may be some people who talk about sigma 8. And why S8? Because again, this is the most precise quantity that we can derive in our surveys. It has the smallest error. And you can also get S8 indirectly from CMB, and you compare. Okay? So S8, why S8? Because it has the smallest error. That's the only reason. So how do we estimate the cosmological parameters? If you remember one of the first slides, I have these easy steps. Those are the easy steps. So you have some data. We collect the data in a data vector. The data vector has the angular correlation functions, the shear correlation function, and the mixed correlation function. Then you have some theoretical modeling for these quantities here, which depends on parameters. Then you have the Gaussian likelihood with some covariance matrix that you have also to find a covariance matrix is not easy, okay? I can tell you that because we worked on that. And finally, you get the posterior distribution of the parameters, which is related to the likelihood function and something called the prior probability distribution of the parameters. Okay, so what is the main issues in modeling correlation functions? Yes. So, can you repeat the question? Okay, so the question is if we use some machine learning in order to... Right. The main analysis, no. And I'm not aware of, in DS, of any method. So we use machine learning for other things like estimating the redshift, photometric redshift distribution, but not for the data analysis itself, as far as I know. Okay? So what are the main issues in this modeling? First, we have to include the photometric redshift uncertainties. So we don't know the redshift very well. So we have to include the uncertainties in the redshift distributions. We don't know the galaxy bias very well. So we have to assume some galaxy bias. This does not affect the shear measurements. Now, the shear measurements are affected by the possibility of having what's called intrinsic alignments, and also the calibration of the shapes, which I didn't have time to talk about. Some baryonic effect, which I talked about in the power spectrum of galaxies, and nonlinear gravity clustering in the power spectrum, which I also talked about. So those are the main issues in the estimation. How are these issues dealt with? They are dealt with the introduction of what's called nuisance parameters that they parameterize our ignorance or the errors in all these things that we don't know. And we actually have to devise what is called the scale cuts to leave out these scales where we don't understand, we cannot model precisely the data. And this is what I meant by saying that we throw out data, but we actually have a scale cut. We say, okay, we don't use this data below this scale just because we cannot model it precisely. So these mitigation methods have to be implemented and tested, and this is a big part of the job of the collaboration, against realistic simulations to validate these methods. And also we should have a requirement of accuracy in recovering the cosmological parameters that are known in the realistic simulation. So this is how we test our pipelines and that everything is working properly. So in the end, we get the most stringent cosmological constraints from a galaxy imaging survey, and combined with external data is the most stringent constraint overall. And we tested this 6-parameter universe, the flat lambda CDM, and as I said, sigma 8 is a derived parameter. So we also test the simplest extension, which is a constant equation of state, W. And I think this is something that I have to tell you. Those are the cosmological parameters that we have, including a possibility of variation of the equation of state. So that's why we have 7. But we have all these extra parameters that we have to introduce in order to parameterize our ignorance about some certain properties. So for each beam, we introduce a constant bias. So that's why we have 4 bias, because we have 4 beams for the galaxy clustering. And then we also have uncertainties in the magnification of the lens, uncertainties in the photometric redshift, uncertainties in the intrinsic alignment, the uncertainties in the photo Z of the position of the galaxies, uncertainties in the shear calibration. So in the end, we have, when we do our Markov chain Monte Carlo, we have to, this goes into the modeling. So we have to take into account all these parameters in the Markov chain Monte Carlo. So it's not only the 6 or 7 cosmological parameters that we have to take into account. It's because we have uncertainties in your modeling. These uncertainties are dealt with these nuisance parameters, and they have to be included in the description. So in the end, it's a huge number of parameters that we have to consider. And we, of course, we marginalize over them to show the results. So the results are usually in 2 dimensions only. So I like this figure a lot. It's a drawing by Jesse Muir, who is a member of a Dark Energy Survey, which kind of shows everything that I told you. So it's the how we do things, okay? So we get some light, some data in a telescope from galaxies. Actually, we have also stars here. So we have images, and there is a way to separate galaxies from stars. The stars are throwing the garbage because we don't care about stars. And then we have all the galaxies, and galaxies, we have to measure the shapes, and then we have to measure the photometric redshift, and we have simulations here. We have different models. We have the covariance matrix, and everything goes into this Markov chain Monte Carlo machine, and out it comes this, what we call the banana plots. Sometimes we call the banana plots, right? It's finished? 2 minutes? Okay. So I just showed the results very quickly. These are the results from Dark Energy Survey. So these are the banana plots, more or less. So this is S8 against omega matter. And you can see that combining the 3 times 2 point functions, you actually decrease the errors. So this is, if you only consider shear correlation functions, it's the blue contours. If you consider clustering plus the mixed one, is the brown contours. If you consider the 3 times 2 is the black contours. And of course, you decrease the error. And the 3 times 2 function, this is the final results. for lambda CDM. This is S8, omega matter, and also sigma 8 if you're interested. And WCDM, you know, W is close to 1. There's a large error because it's only data from DES. And this is consistent with Planck. So this is the results of, again, in black is the fiducial 3 times 2 point function. And in green is the Planck results on these two variables. So there's a metric called tension metric that we can say, okay, these are not in tension, so we can combine them. And when you combine them, you get this very constraining plot here that I showed. Okay, so yeah, so these are the results that you can find. It comes from this very sophisticated analysis. Okay, so I'm finishing. These are my final remarks. I hope to have convinced you that we are entering in a new stage of precision in cosmology with many experiments coming up. Euclid was just launched this month. No, it's going to be great. DESI is doing a fantastic job. LSST will start next year. So can you imagine the amount of data that will be available? It's a great time to be in cosmology. The dark energy survey is finishing the final data analysis. Yeah, that's what I said. The DESI, the dark energy spectroscopic instrument, is performing great with this early data release in June, so last month, with more than 1 million galaxies and quasars. The Euclides satellite launched in July 1st. The Rubin LSST will provide an unprecedented amount of data, and first light is next year. And we have participations from Argentina, Brazil, Chile, and Mexico. That's very exciting. There are more surveys that are planned. So there's something called SphereX and the Roman Space Telescope. There are also CMB, new projects that are planned, the Simons Observatory, the S4. There are amazing opportunities that come together with challenges. There are theoretical challenges of how to better understand the nonlinear regime and galaxy bias or beyond lambda CDM models, for instance. Also, something very interesting is to combine all these things with the new field of gravitational waves. So there's a whole new projects on gravitational waves that are being planned and will come, hopefully will happen. The Einstein Telescope, the Cosmic Explorer, these and the LSST 8 science collaborations are already in full action. Actually, I'm flying to the US on Saturday for the dark energy science collaboration meeting of LSST. So there are many data challenges, data preview catalogs to test modeling, pipelines, etc. So you should get ready for real data. So there are exciting times ahead. You should come and join the fun. And I hope, so this lecture was actually, the idea was to give an introduction to this subject of large-scale structure, just to open your appetite, intellectual appetite, for these things that will be covered in much more detail next week. So I really want to thank you for your attention, and I hope this was useful for you. So gracias, obrigado, and thank you.
I think we can take one question if you have.
We are late, yes.
Recombine, then,
And there's a discussion session today, right?
tomorrow.
It's tomorrow. I will not be here tomorrow. Sorry. So you catch me in the coffee break.
So let's recombine in 12:25.
11:25. Okay.
11:25. Thank you.
All right. Thank you.